Hello. We are working on section 1.1 today, and it is known as the basic concepts. You're going to see the number sets that we have talked about in previous years. Also, just some basic notation. So let's just get started. Sets of numbers. Natural numbers or counting numbers, referring to the same thing. These are the numbers that you just naturally learned how to count. And unless you were a really smart baby, you did not start with 0. You started with 1, 2, 3, 4, 5. So the natural numbers are those numbers starting at 1 and going up to infinity, basically. And they look like that. So go ahead and write that in your notes. The whole numbers do include zeros. So we get just a little bit larger set. 0 is included, plus all those natural numbers that we just spoke of before. Integers are numbers that have both positive and negative whole number style. So -3, -2, -1, 0, 1, 2, 3. The rational numbers, rational numbers, let me get to my pen here. The rational numbers have the word ratio in them. And these are a ratio of two things. So when we think of ratio, we think of a fraction, right? And that is the P over Q, where P and Q are integers. So what does it refer to when it says integers? Well, it's meaning that they're one of these type of numbers. So when I look at rational numbers, I could have the number -2/5. I've got an integer on top, -2, and I've got an integer on the bottom, 5. I could have the number 7 and say that is a rational number. And you're like, wait a minute, I don't see that that's a fraction. Well, very easily we could turn it into a fraction by saying it's 7 over 1. Okay. Irrational numbers. Irrational numbers is a real number that is not a rational number. So that kind of seems jinxy in the way that we define it. Like it's everything that is not a rational number, but that is how it is described. So with rationals, we are able to write them as a fraction. Irrationals, we are not able to write them as fractions. So an irrational number would be pi, for example. I cannot write that as a fraction. Now, 22/7 is close to pi, but it's not exactly pi. Another example, square root of 2. Well, it's about 1.4, but it has a non-repeating decimal to it. Whereas in the rational numbers, like 1/3, they have a repeating decimal. Or like 1/4, they have a terminating decimal. So there's a good example between irrational and rational numbers. The real numbers comprise all of the above topics that we just talked about. So rational numbers and irrational numbers come together to make the real numbers. When we look at the next picture, we're looking at a Venn diagram. And that Venn diagram displays to us that inner smallest group of numbers, the natural numbers, where we started counting at 1, 2, 3, 4, all the way up, and they gave you 27, 45, 99, all kinds of examples. When I move out to whole numbers, now I'm talking about the numbers that are within that, what is it, kind of beigey color. So what would include 0 plus all of the whole numbers, okay? So our world is just expanding more and more. Once I move out to integers, we're in the pink, but the pink will also include the beige as well as the yellow. So I get a bigger complex group of numbers. And then we finally expanded out to rational numbers. Rational numbers do include integers, whole numbers, natural numbers, as well. So we pick up those fractional ones. That's the ones that are outside of integers, 4/9, -5/8. The repeating decimals, we talked about that. The terminating decimals, those are all great examples of rational numbers. Irrational numbers, there's that pi that we talked about. Pi over 4, of course, would be irrational. Square root of 15, not such a nice number. So good examples there. So example 2, it says decide whether the statement is true or false. If it is false, tell why. So some integers are whole numbers. When I see that word some, it only takes 1 or 2 to make this actually happen. And what I would like you to think of is maybe go back to this Venn diagram. Well, whole numbers are within integers, right? So some integers are whole numbers. Yeah. Some integers, because 1, 2, 3, 4, 5 are integers and they are whole numbers. So I guess we get to say true for this one, wouldn't we? Let's see if I can get, this would be true. Every real number is an irrational number. Okay, let's take a peek at our diagram again. Every real number. Well, the real numbers, I'm going to highlight all these real numbers. Real numbers are everything we are looking at there. And I see a very strict division here where every real number is not necessarily irrational. There are some real numbers that are rational numbers. So for that reason, we're going to have to reply false. And let's give an example. So every real number is irrational. Let's use the number 0. Example. 0 is a rational number that is a real number. 0 is not irrational. So we found one counter example to this. 0 is rational, and it still is a real number. Example 3 talks about additive inverses. And let's read what an additive inverse is. For any real number, let's give it the variable a. The number of negative a could be one way you read that. I might read this as the opposite of a is the additive inverse of a. That would mean then that a number and its additive inverse always sum to, I wonder what. Well, let's go over here and name some additive inverses. 5, so let's assign 5 to a. How do I get the other additive inverse? I do the opposite of it, so negative 5. Negative 1/2, its additive inverse would be positive 1/2, the opposite of. Positive 0.3, its additive inverse would be negative 0.3. Now, when I look at the sum of these, what would the sum be? When I add these two together, I'm getting 0. When I add these two together, I'm getting 0. When I add these two together, I'm getting 0. Yes, indeed. They do sum to 0. That looks like a 6. I'm going to stop on that. Let's go back. They sum to 0. So additive inverses, opposite numbers, right? And they give you a number line to see if it's 1, it's negative 1. Equal distance from 0, above and below 0. Simplify by finding the absolute value of each of these. Well, we know that absolute values makes things positive, right? Maybe not things. Maybe I should get a little more specific, huh? How about makes numbers positive? So if I find the absolute value of negative 3, it's going to turn out to be positive 3. B, this would turn out to be 3, but then I've got this additional outside symbol. That means my number is negative, and since it's outside of the absolute value, we will get a negative 3 for an answer. All right, this one, I'm going to transfer over the negative symbol, and then I'm going to evaluate this. The evaluation of the absolute value of negative 3, of course, is 3. So putting it together, I come in with negative 3. Obviously, we get 8 plus 1, giving us 9. D was easy. Here, we want to subtract first, right? Since it's inside a grouping symbol. Yeah, that's right. Absolute values act as grouping symbols. So we want to subtract first, then absolute value it. So I'm going to look at this as the absolute value of 8 minus 1, the absolute value of 7. Now I'm going to do the absolute value, which will take me out to positive 7. Individually, we'll work the absolute values. So this would turn into 20. Copy down the function, which is subtraction. And then this little guy is going to turn out to be 14, positive 14. But since we're in a subtraction mode, it's going to be 6. A little word problem, and I do believe there's a question like this on the test. So when we get done with chapter 1, we've got a chapter 1 test. There's 4 sections in chapter 1. Maybe even just make a star by it. Well, I'm not sure what that was, but that was a star. Which shows, I gotta move myself here so I can see what's below this if I can. Maybe I can't. Which shows the sum and change without regard to sign. Let me look at my notes because I've got the hard copy. Which shows the greater change. Okay, so we're looking for the greater change without regard to sign. So this means it can be either positive or negative. Means either negative or positive change. So I'm just looking down through the numbers, and this one hits me pretty as being the largest number, even though it's a negative. They said without regard to sign. So I would say the cut and sew apparel manufacturing from 2000 to 2012 had the biggest decrease, actually, right? But the greater change. So greatest change. On the test, just be sure to read it carefully because I can't remember if it does without regard to the sign. It may ask just what is the largest change, then I'd want the positive change. All right, inequality symbols, a quick little review of inequality symbols. What do they mean? So this is the not equal sign, isn't it? I think you probably have to write these in. So this is not equal. Less than, the left side is less than the right side. For example, -4 is less than, can't read the number, -1. Greater than. When we add the bar underneath, that makes things a little bit different, doesn't it? Is less than or equal to. So the bar, which is part of the equal sign, now creates an equal to scenario. And then the last one is greater than or equal to. So 6 is less than or equal to 6 is true because we have an or situation, and since it has the equal, it is true. The last one, -8 is greater than -10. Well, greater than or equal to. Because of being greater than, we would say this is true as well. So true or false? You know what? Pause the video, you walk through and write in your answers, and then flip me back on and see if we agree. -2 is less than -3. That would be false. Think of a number line, right? Here's 0, here's -3, here's -2. When a number's to the left of another number, that means it is less than. So -2 is going to be on the right side, it's greater. -1 is greater than -9. Well, here's -1, here's -9. Indeed, farther to the right makes that true. 8 is not equal to 8, that is false. Here, I've got to do a little bit of math first. 12 is greater than 12. Oh, we have to answer false because they are actually equal. A little bit of math calculating here. 10 greater than or equal to 4 plus 6. So I'm getting 10 greater than or equal to 10. Well, because we do have the equal sign, we can say true on this one. And this would turn out to be negative. Absolute value of 3 is negative 3 is greater than negative 3. That's definitely false. Hopefully you got 100% on that. Little quick quiz, right? Graphing. You have done graphing. The other thing we want to make sure we talk about is interval notation. So interval notation includes and doesn't include the endpoint. So if I have a bracket, this includes the endpoint. So you may just want to find a little space on your notes to write that down. If I have a parenthesis, this would exclude or not include, excludes the endpoint. Cool. So when I read this, I have open endpoint, right? It is the excluding type. I do not want to shade in my endpoints. So I'm going to find a different color here. I want to go from -2 to 3. I'm going to leave my circles open since the endpoints are not included. On B, I have a closed endpoint or included. And this one would be open, so excluded. Maybe up here I'm going to write open endpoint and closed endpoint, because I refer to those sometimes as open and closed. All right, -3, I'm going to circle that one, and 1. I want to go between those two. But -3 is closed, so we must do the shading. 1 is open, so no shading, which indicates it's not part of our solution set. On C, I'm reading this as closed endpoint, closed endpoint. Looks like dozed. Hopefully you aren't dozing. Okay, we got closed and closed. 5 to 8. Should we shade them in? Yeah, you're right. Let's shade them in because they are included endpoints. They're closed. The infinity symbol. Infinity symbol will always requires an open endpoint on it. Open sets. That's an E there. So I'm going to use one or the other. Depends on where that infinity symbol is placed. Here we have actually negative infinity up to positive infinity. So we will use open endpoints on both of them. And how am I going to indicate this? Well, basically I've got to show that my arrows continue in both directions. So I'm going to shade this arrow in. I could go all the way to the other end. I'm going to stop right here and just say, you know what? It travels on and on and on. This next one, we are going all the way down to negative infinity. So I'm going to do closed arrow or shaded arrow up to 3. Tell me, folks, closed or opened on 3? Shaded or not shaded? Well, because it is closed, we will shade because it is included in this set. Perfect. On to the last example here. Write in interval notation and graph it. So how do I read this? This gets tricky. People do not like this set notation, but it has a lot of mathematical meaning. When I see the braces, that immediately means set. So I kind of read it as the set of x's. The bar in math actually takes on words such that, I told you it's kind of tricky. So far we have braces, the set of x's such that x is greater than or equal to, I'm writing out everything I'm writing or saying, equal, x is greater or equal to 0. Well, let's graph it because I think the graphing will be easier. 0 is an included endpoint because of the equal sign. And we want everything greater than it. So I will get that. And I'm going to shade my arrow to indicate it travels to the right. Interval notation. So we started at 0. It was a closed endpoint. So I'm going to use the bracket, comma. Well, it travels to the right, never stopping. So I get infinity. And there's only one symbol to use with infinity, and that is an open bracket. All right. Oh, sorry, the lights went off in the room. I'll sit a little bit more in the brightness here. X, it goes, the set of all x is such that -4 is less than or equal to x, which is less than or equal to 2. So we had something mentioned about -4, and we have something mentioned about 2. We want x to be greater than or equal to 4, so shade that baby in. And then open 2 because it's not equal. I do not see a bar underneath there, so it's just open on 2. All the numbers in between are answers, so it looks something like that. Interval notation. This is a closed, and this is an open, isn't it? So I want to go from -4, comma, 2. That is section 1.1, a ton of review. I'm sure many of you are like, would she please go faster? Sorry if it seems slow to you. Section 1.1, page 12. This is your assignment. Notice that you're doing all of those. So 25, 26, 27, 28, all of them. Once you get to 66, you're going to switch to doing the evens. So 66 is down here, and you're just going to race through those. Notice that you are writing it in set and interval notation. I'm sorry, interval notation with graphing. That is somewhat similar to what we were just finishing up with example 8. Okay. If it's false on that one, you want to make it, rewrite each statement so that it uses oh, yes, on this one. I was reading those directions. Rewrite each statement with greater than so that it uses less than instead. Rewrite statements that have less than so that they use greater than. What they want to do is get you familiar with how to flip things. So maybe I don't want, are we doing, I think we're doing evens in this grouping. Let's skip that one. Let's do 74. Do one that you have to do. So for 74, they start us out with 4 is greater than 1. I could switch the greater sign into a less than sign by exchanging my numbers. And that's what they want you to do then. And so read it to yourself. 1 is less than 4. Oh, that's true. So that's what they're asking you to do. Reverse the scenarios, okay? So if I reverse this one, I would say 4 is greater than -9. And I'd have a true statement. So that should be a pretty easy block. I'll slide back up to the top. You should have this on your notes though, but that is the homework. Please use a separate sheet of paper if you do not have a copy of the page that we're looking at. Good day, you guys.